Hello, this is Eric Spiller again, and we're going to be talking about electrostatic particulate separation. Let me bring up the lecture. And here we go. It's moving around on me for some reason, but I believe I have found it here. Here we go. Electrostatic separation for the professional masters, mineral processing. So, of course, you've heard about the electrostatic precipitators in stack and to clean up particulate from stacked gases, things like in coal-fired power plants and smelters. But we use electrostatic separation for particle to particle and particle to particle separation. And there's many examples like pulling out Fe2O3 or hematite, hematitic iron from silica, diamonds, cleaning up coal, feldspar. But by far the biggest one is the separation of zircon from ilmenite out of a heavy mineral beach sand operation. These are alluvial type operations, and in this is the biggest application. In general, what you have is you have a dredge operating on a beach in the olden days, but now they're pretty much inland sand deposits. And on the dredge, you actually have gravity separation that produces a concentrate and a tail that goes back into the pond or whatever it is. And you do this, the concentrate goes to some land-based process. And in this land-based process, we have more gravity separation, we have magnetic separation, we have electrostatic separation, and we might in fact have more gravity separation. They're rather complex circuits, but anyway, so this is the largest use, and it's to recover zircon product from ilmenite and all the other heavy mineral cats and dogs that are in these heavy mineral type deposits. They're also used on salts. So the cleaning up or removing solids from gases really doesn't have much limit on particle size, as long as the particles can be entrained in a gas flow coming out of a boiler or whatever. When we apply it in mineral processing, we're pretty much talking about particles as coarse maybe as 14 mesh and down to maybe 200 mesh or 75 microns. It's not a perfect separation by any means, and so the more narrow the size range going to electrostatic separation, the better you're going to be, the better it will work. We use roughers, scavengers, and cleaner stages, just like in gravity separation and in magnetic separation. Once again, we don't expect a single machine to make both a saleable product and a throwaway tail. We combine them into flow sheets and multiple passes and that sort of thing. It's certainly used in the industrial minerals, like I said, and also there's a lot of electrostatic separation that's used in the food and in the grain industry. The next statement there is just about removing particles from gases. How does this work? Well, Particles have differences in electrical resistivity. They have a resistance to the flow of electric charges depending on the nature of the beast. These differences, it's a code, the conductivity code, and then we classify generally as conductors and non-conductors, and there's some tables that actually also have semiconductors. A conductor has a resistivity of 10 to 5 ohms, and non-conductors have a resistivity of something like 1,014 ohm centimeters, and semiconductors in the range of 1 to 104 ohm centimeters. These are arbitrary definitions, and if you look in your minerals characterization tables, you will see in there that they're generally defined minerals in their pure state are generally defined as either conductors or non-conductors. So what is a conductor? A conductor it allows the instantaneous flow of electric charges under the influence of low electric fields or under low voltage. So there is no internal electric field, and the charges reside uniformly on the surface. So if you have a rock and it's got charges, you have the plus charges or the negative, whichever one you want to go, whatever you want to call it. But the main characteristic is of a conductor is that it loses its charge quickly. So that's a conductor, loses its charge quickly. Non-conductors do not permit flow of electric charges in their interiors. So it starts out that it's not very uniformly charged. You might have a charge here and a charge here. You have a negative charge, and then a bunch more plus charges. It's not very uniform. And there can be a potential difference between this negative and this positive on it, and it takes a while before the charge really evens it out, and so you can have a charged particle and it will stay charged for a period of time on the surface. So historically, in the 1800s, we used electrostatic separation on gold, but then flotation came along, really in 1910, sort of in that sort of era, and so the application of electrostatic separation really faded into the background until it was probably a little more than a laboratory curiosity, but really until Carpenter and his company Carpco in Jacksonville, Florida, during World War II, came up with the high tension separator because of trying to get titanium, primarily from rutile beach sand deposits outside of Jacksonville, Florida, where what is now the home of the PGA, thanks to all the beautiful golf courses there that were, many of which were built on the old workings of these beach sand operations down there. Of course, now you can't, they're pristine beaches and there's no mining going on. Almost all the heavy mineral mining is interior and ancient sands. So there are three types of charging. There's the corona charging, there's induction charging, and there's triboelectric charging. And each one of these has its own machines. By far, the corona charging is the most used in industry. And so we'll talk about that a little bit. You can have a small electrode attached to a corona wire, and you generate a very large direct current voltage drop between that corona wire and the brass tube. And this assembly acts like the beam, and so it produces an ion flow onto a large cylinder which is grounded. I'll show you a picture of this. So particles residing on this cylinder are charged positive or negative, depending on which physics class you took, by the ionic flow. And then both conductors and non-conductors are charged. It doesn't matter whether they're conductors or non-conductors, they all get the charge. So this is kind of how this works. So you have this electrode sitting up here, which remember is a pipe with a wire that's like looking at it here going into your screen. So you have this corona discharge that creates this sort of a cloud here of ions that comes and charges the feed material, the feed, and sometimes we have to heat that up, but we can talk about that later. So it comes onto the surface. This rotating drum is grounded. And so as soon as these particles, they're charged, immediately, remember the conductors will conduct, and so they will lose their charge immediately. So as this wheel turns, it throws off the conductors, throws them off. The non-conductors are pinned against the drum, and they come around here, and eventually they'll get up here, and they may go through a alternating current corona electrode, but certainly they get brushed off and they fall down. So we have the insulators or the non-conductors here. We have sort of the middling here, the mids coming off, and up here we have the conductors coming off in this area. I don't know what else to talk here about. Sometimes we use a lift electrode here that will actually help pull the conductors, up in its path and maybe bring them out a little bit further. So this is a high tension unit with both pin and lift electrodes. This is what one looks like here. This is one version of the electrode, and you can see the products coming off. Here you can kind of see the conductors coming off here and the non-conductors coming around and getting brushed off the drum over here. The issues with electrostatic separation is particle size, capacity indirectly, because you have to have a single layer on that big drum, so a single particle layer on there to make it work. So you have a low feed rate. Temperature can affect the ability to conduct electricity on the surface. So on some minerals, you have to heat it up to get the code to change. And if you look at your, again, mineral characterization table, you'll see some asterisks on there that tell you that the material should be heated up to get to that difference. The specific gravity, because you can imagine that as this drum is turning, if you're trying to throw something off and it's got a high specific gravity, in addition to having lost its charge, it may in fact come down here and it could get confused with the mids. So the specific gravity plays a role in how far the drum throws the conductors off. How pure the minerals is, moisture, surface moisture is bad. The moisture can mess up the conductivity, and that goes for the same as the humidity and the design of materials. So I was going to talk about the other two types of electrostatic separation, and I believe I will in a minute. Bye.